Good evening, ladies and gentlemen. Thank you for coming this evening, and welcome to those from outside the department in particular. We've gone all high-tech in the department, and it's possible to watch the Geotalks because they're being recorded. It's possible to watch them on YouTube now. Ooh. And if you go to School of Geosciences, no, I've got it wrong. Wits Geosciences, YouTube, you'll be able to see the talks. But keep coming along, because you don't get chips and drinks if you're just watching on YouTube. So today we welcome Linda Iaccheri. She comes from Modena in Italy, where she did her undergraduate degree. And then, because jobs for geologists are sparse in Italy, she became a geotech engineer. And then she went off to Germany to be a technician in an isotope lab in Munich. And following that, in 2013, she went to the University of Western Australia in Perth to do her PhD. And she's going to talk to us today about her PhD work. But she joined us in the beginning of October last year to be the lab manager of WIGL. So she's helping in setting up the Wits Isotope facility. So thank you very much to John Hancox from CCIC Cole, as ever, for drinks and chips. We really appreciate them. And Linda, it's all yours.
Thank you, everybody, for being here. As Judith mentioned, these are parts of the results of my PhD study that I did at University of Western Australia under the supervision of Tony Kemp. And I just lose 1 minute to thank the Center for Excellence Core to Crust Fluid System that sponsored part of my analytical work. And then I have to thank the Geoscience Australia and Geological Survey of Western Australia, but because they did part of the geochronology they're going to show today. So I ask you to come here because I'm going to walk you through the results and show you the evidence of rigid crust around 2.5 billion years. And you are wondering why rigid continent is important, why you have to come here and listen to me. Actually, the continental crust is important because it's only present on Earth and not in the solar system. And in particular, the rigid continents played so crust above the sea level played a fundamental role in the evolution of the atmosphere, hydrosphere, and eventually also life. We live on the top part of the Earth, and the crust it is very thin. And although we live on it, we can sample it, we can look at it, the evolution of the continental crust is still under debate. We don't know really how it evolved through Earth history. The model is that the crust is the product of the cooling and differentiation of the mantle. But if I look at the composition of the crust today, that is andesitic, the crust cannot come directly from the mantle. The production of the continental crust happens through a two-stage process. Continental crust forms via a two-stage process. First, we have to do the partial melting of the mantle, and these juvenile melt are going to be injected into the crust. Here, the mafic crust, this mafic melt, are going to stagnate for a while. They are going to go through process of partial melting, and they are going to become more felsic. And this is the way we produce the continental crust today. This is the way it is today, but it could be that the crust was produced in a different way in the past, because the composition of the continental crust changed throughout history. In particular, is evidence of variation around 2.5. A 2.5 it represents the boundary between the Archean and the Proterozoic. It's marked by fundamental changes in the atmosphere, hydrosphere, lithosphere, and mantle. The Great Oxidation Event marks the shift from anoxic to oxic atmosphere. Is happening at the same time when seawater change composition, shift composition from the mantle that is recorded by the strontium isotopes. There is an increased evidence of reworking of sediments into the crust, and this is recorded by the oxygen in zircon. The continental crust, as I mentioned, changed composition, shifted from more mafic to more felsic, and there is also an apparent decrease of percentage of mantle melt, and this is evident because we have the disappearance of the komatiite. These variations show that the evolution of the interior of the Earth and the evolution of the exterior are interlinked, but the process that is behind this transition is still not clear, is still cryptic. Most of the attempt to explain this transition, they look into the cause, into the mantle. The mantle cooled and triggered variation upward. However, even if there are changes in the condition on the surface, they can trigger variation downward. And there is a numerical model that shows that if the surface temperature decreases, the plates behaves more rigidly, the plates move more fast, they are more fast, and move more fast, and this triggers cooling of the mantle and also triggers the cooling of the atmosphere. So between the exterior of the Earth and the interior, we have the crust. This is my interest. And if I find a way to monitor how the crust change, and how can I find this? And the composition of the crust depends on magmatic processes, on partial melting, but it also depends on the source that I'm melting at that time. So I have to find a way to monitor variation of magma sources around this time. And to do this, we are going to use the Detrital zircon from the North Australian Craton. The North Australian Craton occupies a large part of Australia. If you look at this map, most is gray and white. The gray is Paleoproterozoic origin. The white is a younger sedimentary basin. The oldest rock are very tiny in layer, and they are Neo-Archean, and they are embedded between the Paleoproterozoic. The relationship between Neo-Archean and Paleoproterozoic is not understood because there is no exposure. As well, there is no clear understanding of the relationship between the different origins for the same reason. This is the North Australian Craton. There is no exposure, it's very flat, very remote, there is no road. I could go there in 2003 just because there is some gold mining and they gave me this truck and the facility. Otherwise, there is no way to have food or gasoline. And especially it's very remote, but mostly of all, there is no exposure, it's flat. So the problem of the North Australian Craton to understand how we evolve with time is complicated because we don't know, first of all, what is the basement. Is the Neo-Archean the basement? We don't know. And we don't know if there are different crustal blocks. The Paleoproterozoic assembling of the North Australian Craton has been explained in two different ways. One is an intracratonic tectonic model. And other are modern style plate tectonic. And the intracratonic model is kind of old-fashioned. Idea is of the formation of small mantle cell that trigger rifting of the crust. We have mafic melts intruding into the crust, and then eventually we have basin formation with the position of sediment. And then when the mantle cell cools down, we have the closure of this basin. The other model of the assembly of the North Australian Craton is modern style plate tectonic, and where we see a map of dismembered Australia with two subduction going on at the same time. And the problem is that this suture, we don't know the suture, we don't know the crustal block. So also the modern style plate tectonic have some weakness because we don't know where are the different blocks, where are the different suture. So for this study, I mentioned that we are going to use the detrital zircon, and the Paleoproterozoic origin are characterized by the assemblage of turbidite, so metasediment intruded by granites. We are going to use the detrital zircon from 4 different origins, from the Pine Creek, Horse Creek, Granite Stanamine, and Aileron. And these detrital were deposited before 1.8. So these detrital zircon are showing us the erosion of a crust that was exposed in this part of the world before 1.8. Since we don't know the relationship between the origin, at the moment the origin are all studied independently. The stratigraphy of the metasediment is fairly well characterized for each origin, although we don't know the correlation between the different units. And we are going to use the detrital zircon deposited before 1.8. Here is the geochronology. The geochronology has been used for making the stratigraphy of the paleosedimentary sequence. The lower units are characterized by a major peak of 2.5. This major peak at 2.5 disappears going up in the sedimentary sequence. It becomes smaller and then eventually disappears, whereas we have a peak at 1.87, it becomes prominent. If I look at the summary of the detrital zircon, if I put all the data together, I see that the detrital zircon record the erosion of a crust that is forming 3 major events, at 2.7, at 2.5, and 1.87. And when I see these 3 peaks, I can see that there is a correlation with the global zircon record. That's the interpretation of this peak distribution of the zircon record is debated. For some authors, these peaks represent the evidence that the formation of the crust was not continuous throughout Earth history, but it's been episodic. For other authors, this peak represents a peak of mantle activity, plume activity. And for other people, from other authors, the peak distribution represents an artifact of preservation. So the crust is being produced throughout Earth history, but these are episodes of preferential preservation of the crust. And these are also correlating with supercontinent. We are going to use the detrital zircon for understanding if we are going to deal with crustal recycle or crustal formation in the North Australian Craton. So the geochronology was done by shrimp that give us the crystallization age of the zircon. On the same spot, we have done SIMS for determination of the oxygen isotope. The oxygen isotope is a stable isotope, is time independent, but he records if the zircon had been exposed to superficial process before partial melting. And then on top of, we are going to determine the hafnium isotope composition that is going to give us an idea of crustal mantle differentiation processes. So this is the total of the results. And we see that we have major arrays in correspondence of the 3 major peaks. Before to interpret the results, I give you a background. And if I imagine to produce a melt at 2.5, a melt from the mantle, this zircon is going to have an epsilon hafnium that falls on the depleted mantle array because it comes from the mantle. And it's going to have an oxygen composition that falls within the mantle-like because it's never been exposed to surface processes. It comes from the mantle. The same at 1.87, depleted mantle, mantle-like. If I'm going to rework crust that is clay-rich, this crust has a negative or unradiogenic hafnium because they are reworking a crust that is old, so away from the mantle. And this crust is clay-rich. It's been through a surface process, so it's going to have high or heavy oxygen isotopes. If I'm going to rework a crust that is old but has never been exposed to surface processes, this zircon is going to have unradiogenic epsilon hafnium composition, and is going to be coupled with mantle-like oxygen because there's never been on the surface. So this is just the bearings, how to see this diagram. So keeping this in mind, we see that the detrital zircon that have a crystallization age older than 2.7 show scattered epsilon hafnium, but they have mostly mantle-like oxygen composition. The array at 2.5 is very wide. I go from the depleted mantle to very unradiogenic composition. And this large variation in epsilon hafnium composition is coupled with a very restricted composition in oxygen, mantle-like or slightly heavier. When we go on the magmatic event at 1.87, we see that the array in hafnium is restricted, is much smaller than what we saw at 2.5, but we see a shift in the composition of the oxygen. Very few zircon fall in the mantle-like, most of the zircon show heavy oxygen composition. So there is, if I look at the two array, I don't see a clear, simple evolution trend from the magmatic source of 2.5 and 1.87. I would expect to see more data in this part of the diagram if I would have a linear reworking of all crust. So before to make any interpretation on the sources of the melt, I want to know where the detrital zircon come. So I compare the results of the detrital zircon with some igneous exposure of that time of the North Australian Craton. And here are the Neo-Archean exposure. So in gray, we see here in the background the detrital zircon, and these colorful are the igneous, meta-igneous sample. We see that most of the detrital zircon actually are overlapping with the igneous exposure. It's here in the central part and here for the Paleoproterozoic. So in general, the detrital zircon have local provenance, although we see that most of the other detrital zircon actually don't have a direct meta-igneous counterpart. So it could be that these rocks come from a different continent, that it's not the North Australian Craton. Some people think that there is a provenance from India. Or it could be that some of these meta-igneous are not preserved anymore, or maybe they are buried and we just cannot see it. I wanted to know where is this provenance. Since in Australia we have a lot of Archean, I wanted to know where the detrital zircon come from. I have an Archean, local Archean provenance. Here we compared in gray the result of the detrital zircon, and then we have a sample from the Pilbara and a sample from the Naria terrain that is in the Ilgan. And I see that there is very little overlap. Very few detrital zircon come from the Ilgan and the Pilbara, and actually this is coherent with the model that 1.8 the Ilgan and the Pilbara were far away from the North Australian Craton. So we see what is the magma source at 2.5. So this large array of epsilon hafnium composition tells me that there is a partial, in this magmatic event at 2.5, we have the partial melting of a very heterogeneous crust. There is limited depleted mantle input. Very few grain falls on the depleted mantle array, so limited depleted mantle and so limited crustal growth. Since the detrital zircon have an oxygen that is mantle-like or slightly heavy, I think that the reworking of the crust was happening within the crust. I was working material that was mostly in the crust and very little material that was sediment, although I cannot exclude sediment reworking. I was wondering if I could understand actually what kind of material I'm reworking, and we need to keep in mind that the lutetium-hafnium ratio of the zircon does not correspond with the lutetium-hafnium ratio of the host rock, because when the zircon crystallizes as very little, encapsulate a lot of hafnium, the substituted zirconium, but has very little lutetium. The only way to understand which kind of rock I'm going to rework is if I can see a linear trend. And in this case, the detrital zircon define a trend. I can speculate that this detrital zircon represent the reworking of a same source. And if this is the case, the slope gives me a Lutetian affluoration of 0.014 that correspond to an average continental crust. So I'm reworking a normal continental crust. And another question that came into my mind is, if I rework so much crust already at 2.5, why I have very few detrital zircon with the older age in 2.5? And so this can be explained if the magmatic event at 2.5 is very high in temperature, so that the old zircon had been completely melted away, the uranium lead clock has been reset, and the new zircon have inherited a Lutetian affluent from the melt. Or it could be that what part of the crust that I'm reworking at 2.5 was mafic, and so it was already poor in zircon to begin with. So now we look at the sources of the 1.87 melt. We saw a continuous restricted array in epsilon affluent. There is no detrital zircon that fallen on the mantle array, so I don't have evidence of formation of juvenile ments from the mantle. So mostly of the crust is reworking, and since the oxygen is heavy, I am reworking supracrustal material. I'm reworking sediment. The information that I'm reworking sediment 1.8 in the Paleoproterozoic gives me the idea that this intracratonic model that were done for the North Australian Craton are actually not feasible, because this model, they see in the partial melting of mantle that actually we don't see in our array. So the magma sources 1.87 are relatively whole and exposed to surface processes. And I'm wondering, can the 2.5 crust represents the source of the 1.87? And it could be that this part of the data could trajectory and explain and be reworked at 1.87. So this part of the crust can be reworked at 1.87, but it's not a straight reworking. I need to expose this crust on the surface, expose to surface processes, make a sediment, and then reworking. Could this restricted array represent a mixture between the mantle in melts and a melt that would sit here for reworking of very old crust? And I interpret that this is not possible, because if I have so much mantle injection in melt that would drag isotope composition from very negative to more radiogenic, to less radiogenic, this would also drag my oxygen toward mantle-like, and we don't see. So could this array represent an homogenization, but not by magma mixing, but by sedimentary processes? And this is my interpretation. So if I take this heterogeneous near-Archean crust and I expose it on the surface, and I make a sediment out of it, and I melt the sediment, I'm going to have an epsilon affluent that is hybrid, is homogeneous, and is going to have heavy oxygen. So if I look at the variation of magma sources, we see at 2.5 the dominant intracrustal working of an heterogeneous crust with limited crustal growth and limited reworking of sediments, where at 1.87 we have a dominant reworking of sediment with limited not juvenile addition. So for the partial melt at 1.87 we need to have established sediment. This implies that after 2.5 we need to have proper continent. The crust must be rigid, because we need to have the uplift, mantle building, erosion, transport, and the transportation is going to mix the sediment, blend the sediment, and eventually I'm going to do the partial melting. This shift in the mechanical behavior of the lithosphere actually is predicted by numerical model. is been also interpreted by the increase in erosion flux in seawater and from the shift from subaqueous to subaerial volcanism. So in summary, the detrital zircon define 3 major peaks, and these peaks are mostly episodes of crustal reworking and very little crustal formation. This means that most of the crust of the North Australian Craton was formed by 2.5, although this crust actually is not exposed at the moment. The apparent decrease of crustal generation is happening at the same time when we have an increase of crustal reworking. And this means that the crust after 2.5 was rigid enough to allow the establishment of sedimentary processes. And this mechanic and this shift in mechanical behavior of the lithosphere is also increase in the cooling of the atmosphere and in the efficiency of the modern style deep subduction. Thank you.
Right, I'm told I have to use the microphone. Are there questions for Linda? Oh, go on, it's you.
I was waiting for permission. Linda, great. So, but the Pilbara Craton is modelled as maybe being attached to the Carpal Craton as well, where at what 2.7 all the way down through what we call the Transvaal Paleoproterozoic. So there's obviously got to be a rigidity to parts of the crust in Australia and parts of the crust in Southern Africa. What would be the differences? Have you looked at the differences on the Pilbara Craton or even on the Carpal Craton on its sedimentary sequences? Same sorts of studies done. Do they give different timings? That there was maybe softer crust early on, but by Archean times it was Paleozoic.
Yeah.
In Archean times it was already rigid to produce the Wits Basin and the Transvaal.
Yeah, I just have to repeat quickly the question because sure. We cannot record this. You're mentioning that it could be that the crust was already rigid because the Craton were already together and we were making the basin. I think that the basin were not deep. They were just very shallow.
But have you looked at the pattern of similar hafnium and oxygen isotope patterns from Witwatersrand sediments or from Transvaal supergroup sediments to see whether?
No, in this particular I have no look, and for sure it could be an opportunity if someone has data or to look into that. But I think that the crust in the Pilbara, that I don't know now the age of the Capval for the Pilbara is older than 3 billion, and the crust, it was not making big mountain ranges. It was not sustaining itself.
Are there further questions for Linda?
Thank you. That's the first time I've actually appreciated how useful delta ATO and combined with excellent hafnium is in zircon. The diagrams you showed seem to be sort of similar that so many people show in talks of this type. Has anyone ever plotted for a particular time span delta 18O against hafnium?
Yeah, sure.
And so just a simple sort of XY for 2.5, 1.87, etc. Do you see particular linear arrays with that sort of diagram? And can you
Okay, there's the diagram where they compare oxygen and hafnium on that zircon, but you have to do with zircon population the same age. because of the ways it doesn't make sense. There are studies that they use that. In this case, if I do this plot, and I did it, they are just clustered, they are all over the show. But in other situations, they could give trends, and sometimes they give mixing trends, especially if you have a mixing between two end members, you are going to have an array of data. But in this case, I don't have a mixing. This zircon, I don't think they are due to magma mixing, and they are scattered all over. They make a cloud. They have no significance. But there are, if one has oxygen and hafnium data, for sure you can plot them together. One has just to bear in mind to keep zircon of the same age population together. Yeah.
Roger.
Okay. I didn't realize the significance of considering the models that you said at the start, but after seeing the data. So your first event, you want massive reworking, but you don't want any major orogeny. Or could you have had a major orogeny and everything got stripped off and ended up somewhere else? I mean, these are pieces of crust, they're not the whole continent. So if you had the major reworking, surely there must be some sort of plume-like model that would apply without getting lots and lots of thickening of the crust.
I'm reworking crust that is very heterogeneous. Okay, here there is different color that is a little bit maybe complicated to see, but different sedimentary units are a collection of is very local. The Archean crust, this is for Nostrosil and Craton, and it could be that for other Craton is different, is very local. These sediments are picking up this kind of crust, and another basin I'm going to collect this Archean, and in this I'm going to have this. So different color are different unit, and since in different location I'm actually eroding a crust that is being done in the same magmatic event, but is very heterogeneous, it's very local, and I'm reworking this crust at the same time. The only thing that I see is that there is oxygen that tells me that there is no superficial processes happening. But this is actually a little bit biased because there is before the great oxidation event, and we don't know really what was the signature of sediment before the oxygenation. So it could be the sediment at that time had the same signature as the mantle because the seawater has the mantle signature. And so here, if I go in the systematic of oxygen, I exclude the sediment. I say there is no much sediment, but I cannot exclude it completely because actually the oxygen is blind. The oxygen at 2.5 doesn't see a sediment because of the mass fractionation of the oxygen. There was anoxic atmosphere, anoxic ocean, so the oxygen was not behaving in rocks like it's behaving today. Yeah.
So do you see any zone zircons in that population where the core is perhaps
This zircon have very few core rim. Very few core rim. Yeah.
Is that expected if you're reworking older crust? Would you not expect to see some older cores?
Yeah, this is why I was wondering why, and I was thinking, oh, maybe part of this crust was mafic and was poor in zircon to begin with, although old. Or the magmatic event at 2.5 was alkaline or very high temperature, and this is why the zircon had been melted away. I was also, when I saw the results and I saw reworking of very old crust, I also was wondering, why do I see very few core? Why do I have very few zircon that are old? So the way I could explain it is maybe some of the crust is mafic.
Okay, thank you, Linda. I think I'm going to stop there. Thank you very much indeed.
Thank you.
Our geotalk next week is from another new member of staff. Glenn Nawila will be talking on highly siderophile element concentrations in Archean and Paleoproterozoic marine shales of the Cap Val Craton. So it seems like an interesting follow-on from Linda's talk. So thank you very much. Hope to see you all next week.